All right, guys, so we're going to take a look at the actual applications of exponential functions today. Okay, so we're basically going to take some stock equations and then apply them to word problems so we actually answer some important things. Okay, so there are many important applications of exponential functions in the field of science and finance. Okay, so we're going to go into financials after this. Okay, but there's also, you'll notice how it's a little difficult to fit quadratics to all sorts of different scenarios in the real world, but exponentials, a lot of the things we see in the real world behave in a nonlinear way for sure, but also it's tough to model everything with a quadratic. You'll see quite a few different kinds of applications of exponentials, as we'll see today, right? But it's a little easier to fit an exponential curve to real world examples relative to the quadratics, right? I don't think there's not as much limitations to the exponentials. Okay, so let's take a look at a couple examples here and we'll work through some of these. Okay, so properties of exponential growth, okay? So remember, if we recall, okay, we have two different things going on here, okay? We have two different axes, right? One is the x and one is y, okay? Whenever we produce graphs, we have something like on the x-axis, we normally have time. Well, time is independent. This is how I remember this, okay? So things happen in time. Time does not stop, right? So it's independent, right? Okay. And then we have dependent things. So things that depend on what happens with the independent variable, okay? So this, we could also call this our input, right? And this will be our dependent variable, okay, y. So then basically with exponentials, we see some sort of curve like this. So exponential growth specifically, okay, as the independent variable increases, okay, so as I increase the independent variable x, I'm going to see an increase in the dependent one. So all that means is the graph is going to look something like this, okay? So as I increase time, for instance, the ball is going to get higher and higher and higher and higher and higher, whatever it is, okay? So that's just the notion. That might not be the best example, but that's kind of what we're building towards, okay? So in exponential growth, the rate of change increases over time. So how quickly something is getting higher and higher can be modeled with an exponential, okay? So in other words, the rate of growth becomes faster and faster, okay, as time passes, okay? So the exact opposite thing happens for exponential decay, right? So we can use the exact same axes, right? Dependent and independent, except this time, our curve is going to look something like this. So as time goes on, we get closer and closer and closer to this axis, right? So it actually, as time goes on, it decreases and decreases and decreases, okay? That's what we call exponential decay, okay? So another way to put that would be the rate of decay becomes slower as time passes, okay? So we basically have kind of two kinds of questions that we're going to see. And from that, we're able to answer different kinds of questions, okay? So we're going to see growth questions and we're going to see decay questions, but sometimes things in a little bit of a science aspect, right? Things behave in a way that you've heard of half-life, hopefully, in your science classes, right? Or a doubling rate, right? So we're going to have equations that deal specifically with those scenarios, okay? But we're also going to have some growth or appreciation or depreciation questions too, right? So things that that grow, but just not necessarily doubling, right? So one of the questions down here would be like, how much is a computer worth after so much time, right? Well, it's decreasing by some percentage every year that you own it, okay? So R is going to be the percent represents the rate at which the quantity increases or decreases, okay? R must be converted to a decimal. This is very, very important. Okay, you cannot just plug the percentage in. Okay, that's one of the key features of making these work. Okay, and then we're going to have two other variables here. You'll see N naught and M naught are the initial amounts at time equals 0. Okay, that's what we denote this as. This is N naught, so starting time, right? Something like that. Okay, so that's kind of the gist of this. Okay, and really this makes a lot more sense once we actually start doing questions. Okay, so you're going to see here the 4 equations. Okay, and they all look pretty similar. Okay, this one here you can know as being the doubling because there's a factor of 2. This one here is going to be the half-life question or equation, right? Because it's got the half there, right? So that's how I'd memorize these two. And then these two up here, these are appreciation and depreciation, okay, or growth and decline, right? Decline, I see the minus sign. Growth, I see the plus, okay? And we're going to see how these actually work when we start doing some questions down here, okay? So really the key to this is knowing what your variables stand for, how to extract them from the equation or the question from words, and then being able to answer it. Okay, so let's just take a look here. I'm going to show you the best process to do this in, I think, anyway. Step 1 for me is always, let's write down what I know. Okay, and so I'm going to go through this list here, and I'm just going to read the question first of all, right? So the population of Basel Island is currently 102 people, okay, and it's growing. This is a key word, growing. You can hack up whatever question you want, or like the questions however you see fit, right? It's growing at 15% per year, okay? My job, or your question, is to predict the population on this island after 3 years have gone by, okay? So I see kind of growing, okay? It's not necessarily growing at a doubling rate, right? So I know I'm dealing with this particular equation. So then I shoot over and I'm like, okay, well, what do I need to know? Well, let's first write out the equation, okay? We can do that before we do this list. Let's write it out. So N equals N naught multiplied by 1 plus R to the power of T. Okay, and so your job here is going to be able to, or is for you to be able to answer whatever it is they're asking you, obviously, right? But in order to do that, you need to know what each of these variables are from the question, right? So the information that they're providing you, which is why the first thing I always do, okay, is I write down the things I know and I don't know. So N naught, we said, was the current condition, right? So where we're starting, initial amounts, okay? That's what we said up top, okay? So let's go down here. N naught is going to be 102 people in this question. So N naught is equal to 102, okay? Now, let's keep reading. It's growing at a rate of 15%. So R is going to equal 15%, but remember, I cannot leave it as 15%. It needs to be converted to a decimal. How do I convert percentages to decimals? I divide the percentage number, so 15 divided by 100. Okay, so that's going to be equal to 0.15. That's the R value. Okay, now predict the population on this island 3 years from now. Okay, well, they're telling you the time. Time equals 3 years. Okay, and so the last thing you need to know, I see that I filled in N naught, right? I know N naught, I know R is 0.15, and I know T. So the only thing left to solve for is N, which happens to be predict the population after these conditions, right? That's all you're doing. You're just selecting the correct equation that's going to give you the right answer, okay? So the last thing you want to know is you're going to write down N naught, n equals question mark. That's what I want to know. So let's plug in our information. I'll show you how to do this. This is actually not too bad. So n is equal to 102 multiplied by, what do I have to plug in? 1 plus r goes in for, or r is the rate, so 0.15, and t is going to be 3. Okay, so n is going to equal 102 multiplied by, I'm going to do the math on this section inside the brackets, and that's going to turn into 1.15 to the exponent of 3. Okay, now I'm going to show you something. Okay, you can go to your calculator. This is how this works. Okay, you have to take care of this first, the exponent. You cannot multiply this in. Do not do this. Not allowed. You're not allowed to do that. Okay, so what you have to do is take care of the exponent on the number that's inside of the bracket. So let's go to our calculator. Okay, I have a number on the inside of the bracket of 1.15. Okay, that is raised to the power of 3, so cubed. If you have an iPhone, you'll have that button, right? So that's the number. So it's going to be n is equal to 102 multiplied by, okay, 1.58, I believe is what it was, 1.52. Okay, now I'm going to show you, just so everybody's not confused, okay? This math that you did right here is this number. Okay, now the last step here to figure out what the new population is going to be after 3 years is to actually do the math on this. Okay, so go to your calculator. You're going to have 1.52 multiplied by 102 was the initial. Yep. Okay, multiplied by 102. There you go. So it should be 155. N equals 155. And then your last step here is going to be, therefore, the population after 3 years is 155. Okay, not too bad. Okay, so you're actually able to answer something about a particular population growing after some amount of time under some conditions, right? That could very easily be declining at 15% per year, right? And then you'd have a smaller number at the end, right? Okay, so let's take a look at this one. Bigger numbers this time, okay? Bigger numbers, but also a different style of question, okay? So let's take a look at this. So in 1980, the frog population on Bosco Island was 5,000 and been doubling every 7 years, okay? So I'm just going to throw some highlights on some important things, like words that you're looking for when you do these questions, 7 years. If this trend continues, write a formula for how the population will change starting in 1980, okay? And then it says use t equals 0 for this condition, okay? Okay, so let's write an equation. That'll be like the first part. So let's write down some things. We go to our first step here. N equals, I don't know, okay? But I do know what's this. This is N naught, right? It's the initial population, right? So N naught is equal to 5,000, okay? Okay. And then it looks like, oh, it's telling me that something doubling. Well, if I see the word doubling, I'm saying there's a factor of 2. So it's multiplying by 2 every 7 years. So this no longer looks like, you can see hopefully that this kind of clashes with how this question is worded, right? It's not the same. So let's go back up to our thing here. I see a doubling equation. Just because this is bacterial growth doesn't matter. The important part is using the word doubling, right? And so when I look at the equation, I get something like this. Okay, so let's go look at this then. So n is equal to unknown. This is what I'm trying to find, right? And naught was 5,000, okay? So let's write the equation. Okay, now here comes the tricky part. This is a little bit tricky. Okay. We have this t over d notion, okay, where t is going to be time, and d is going to be the doubling. So how long it takes to double, okay? And we're going to see here for a sec, okay? So that's the equation, okay, that we've selected, okay? Now, our job now is to fill in the information. Okay, so I know the doubling factor, okay, is going to be 7. Okay, but my job is to figure out where to put it, okay? So I see doubling every 7 years. Okay, so every 7 years, so let's say 7 years passes by, the new population is going to be 5,000 times 2, which would be 10,000, right? So the d value, doubling, is 7. Okay. Now, the last thing you have to figure out here is the t value. Okay. Well, turns out it wants to know, if we start in 1980, how much time passes until we reach the year 2002. Well, 1980 plus 20 would reach 2000, plus another 2 would be 22, right? So our t value is going to be 22. And now you have your list of knowns and unknowns. You plug them into the equation first. That's your first step, okay? Then you can deal with whatever's going on afterwards. So let's do that. N, I don't know, okay? Then I can go, and naught is 5,000 multiplied by 2. And then I go, t is going to be 22 divided by 7. Okay? Now, much like the last question, you're kind of in a predicament here. So that's not, sorry, I should write this a little bit neater here so nobody gets confused. This is to the exponent of, okay? Let me move this down. Okay, so this is actually to, let me delete this. I'll rewrite it. T over d. It's to the exponent, right? So when I write this, it's going to be 22 over 7. So your job here, when you're doing this, n is going to equal 5,000, okay, 2, but you got to do the math on the exponent first. So you got to go to your calculator and go 22 divided by 7 is going to be 3.14. You can write that in there. 3.14. Now, much like the last question, you cannot multiply this in there. Do not do that. Okay? You have to first do the math on the exponent and the base, right? So let's go, so it's going to be 2. Okay, and this is how this works. You got a button over here. It's x to the y. You can see it underneath the big 2 there. And then you're going to go, okay, I need my exponent to be 3.14. Right, so let's go back to our calculator. The exponent 3.14, that's 8.82, okay? So our next line here is going to be n is equal to 5,000 multiplied by 8.82. Okay, this red highlight is the math that was done from 2 to the exponent of 3.14. Now, your final step is take 8.82. 8.82 multiplied by 5,000. 44,100. Okay. Now your last step. Therefore, the frog population after 22 years will be 44,100 frogs. Okay, so I'm going to take a little break here, and then I'll do part 2 so you guys can have a full understanding. What you're going to see here, okay, with these particular questions, we saw growth, like things growing, right? We're going to see in the next 2 examples or 3 examples,